seem very similar to a lot of the big AI words you're hearing these days about building large language models or large foundation models. And I want to take the next hour or so to highlight a nuance and motivate the need for this concept of large population models so that we can do more realistic, secure, and reliable decisions.
You want mute.
Hi, was I on mute? Should I start again? Can you hear me? Can you just? Yeah, I don't think I can see the chat. So if anybody can make a comment.
Yes, we can hear you.
Okay, perfect. Yeah. Perfect. So yeah, so I'll just get started. Okay, perfect. Yeah. So I wanted to talk to you guys today about this concept of large population models. Semantically, it's similar to a lot of the big AI words we're hearing today about large language models or large foundation models that have sort of taken up a lot of the modern discourse around AI. And I want to talk about these ideas to highlight an important nuance on the need to build large population models that can help us do more realistic, secure, and reliable decision making for large populations in context of many of the problems that Alvaro mentioned in the beginning. So let me get started. To start with, I want to start this conversation with a simple motivating example. Consider, for instance, that we're at the beginning of the pandemic, of the COVID-19 pandemic, back in early 2020, when we finally figured out tests as a means to detect infectious individuals. So if you ask an individual, what kind of a COVID test do you want? Each individual wants the most accurate test. Since the government's policy is if you're infected, you have to quarantine. So as an individual, my incentive is if I'm infected, I want to know. If I'm not, I would much rather not quarantine. So the specificity or the accuracy of a test is of paramount interest to every individual in a population. So any smart, rationally thinking individual would pick, give me the most accurate test. But when the government needs to make this kind of a decision for the entire population, the incentives and considerations change. So they don't necessarily need to think about the incentives of a single individual, but they care more about reducing the total number of infections in that population. In that case, when I'm trying to deploy an intervention to a population, I need to think about both dimensions. I obviously need to think about the properties of the intervention. How good is the test? How fast is the test result? But I also need to think about the properties of the population. People move around, infect each other, and a lot of these passive interactions cause rapid transmission of infection over a population. For instance, in this case, we realized that to counter against this rapid spread of an infection, the turnaround time of a test result can actually be a more important measure than the accuracy of a test. So this is slightly counterintuitive, where the population outcome can be drastically different from the sum of individual choices. For instance, this is the reason why in a lot of countries we had huge push for rapid point of care tests, even though RT-PCR tests would have been more accurate during COVID. So what we realize is that what's good for a population may not necessarily be obvious by observing an individual in the population. So to be able to make decisions for large populations, we need to be able to model the collective behavior of interactive individuals in these large heterogeneous populations. So and that's sort of the focus of a lot of our research, that how do we build generative tools to help us realize these kinds of decisions. So a lot of the current discourse around capturing behavior of individuals has centered around the idea of using large language or large foundation models that try to regress on billion scale internet data to help you make decisions. For instance, if you just go to ChatGPT, given some context, and ask a similar question, let's say in the context of a vaccination policy. Does it make sense to delay the second dose of a vaccine? For an individual, it does not. But for a population, it might. So if you ask this kind of question to ChatGPT, you'll get an extremely long and verbose answer. So these foundation models can be realistic in terms of capturing some essence of behavior because they've been trained on billion scale internet data and are obviously very expressive, but they tend to be extremely unreliable. very verbose and prone to hallucination, and also extremely expensive to scale and deploy. So when making decisions for large populations, often in resource constrained environments, for instance, when trying to tackle a pandemic or work against a wildfire, we need principled understanding, quantitative results, and hallucination-free analysis, and all of these capabilities in a very practical ecosystem. The other dimension of people looking at trying to capture behavior, look at this dimension of research called agent-based modeling. So agent-based models are like a class of very mechanistic model that try to simulate heterogeneous populations by modeling the bottom-up local interactions of agents. So these ideas are very relevant across several disciplines. Like agent-based models are used across biological, physical, digital realms, as agents can be cells in a tumor microenvironment that interact with each other and spread tumors, humans in the physical environment that move around, spread infection, or even avatars on a digital social network that are spreading influence and information. So agent-based models are extremely powerful way to capture the behavior of large populations, model interaction dynamics, and they provide a mechanism to incorporate principled domain understanding into simulations. So they can be extremely useful for decision making, especially in population contexts, but they're often very slow and tend to model unrealistic scenarios. So what we really need are agent-based models that can recreate million-scale populations with extreme detail and seamlessly integrate with real-world data streams. So a lot of the focus of our research in large population models is to bridge these two diverse worlds of large foundation models and agent-based models by rethinking principles behind agent-based models, which are mechanistically interpretable in this modern world of data-driven large-scale machine learning and AI research. And that's a lot of the research that I'll be talking about, that how do we bring these two worlds together to have mechanistically simple and interpretable, but extremely rich and powerful computational models to help us make decisions for large populations. So yeah, before going into details, I want to give a quick background about myself. So I'm a PhD candidate at the MIT Media Lab. A lot of my research has focused on bridging these worlds of machine learning and simulations, and previously in the context of imaging to solve a wide variety of inverse problems, and more recently for agent-based modeling. For instance, in the past, I focused on bridging machine learning and imaging to help us try on clothes in the browser, where you could estimate the 3D shape of a person by looking at a single image, or to build cameras that can help you look around corners, see through fog. And a lot of my recent research is focused on how can we translate a lot of these insights that we've built along the way for bridging machine learning and simulations to help us design more realistic, fast, and reliable population simulation models. And that's going to be largely the focus of my talk. And I'll try to highlight some of the fundamental technical ideas that we've been working on in this discipline. And I'll ground this in the context of a case study for epidemiology. And towards the end, I'll also talk about our platform called Agent Torch, which you can just pip install Agent Torch, which allows you to build these large population models for yourself. And I would love to end with a discussion of some open problems and ways in which we could work together if you're interested. Okay. To give you some context, the primary motivation behind our research has been to rethink a lot of the work in agent-based simulation models in the modern AI world. To do that, we start with first principles and think, how do we want to redesign agent-based simulations? And the key insight is we want scalable and differentiable agent-based simulations. Specifically, a lot of our platforms in large population models focus on designing tensorized and differentiable simulations that can help us achieve fast forward and differentiable inverse simulations. So basically, large population models allow us to realistically simulate large populations very quickly. So you can simulate few million agents, millions of agent interactions in few seconds on a GPU. And I'll show how we use these tools to sort of calibrate these models more efficiently to real world data streams using ideas from automatic differentiation and by integrating deep neural networks. I'll also present some results which I really like, where we can actually validate the results of simulations without ever having to run any simulations using ideas from differentiability. And in a sense, we can use a lot of these tools to execute digital experiments and design strategies for large populations at real world scale. So I'll show some case studies where you can use agent-based models to evaluate prospective interventions. For instance, if you're sitting at the beginning of the pandemic thinking, what if we delay second dose of the vaccine, or what's going to be a good vaccination protocol, when should we reopen schools? And also analyze retrospective decisions. Like sitting today, could we say how effective really were lockdowns? What could we have done differently? So I'll present mechanisms where we can do granular understanding of these kinds of decisions at scale for really large populations. And when we deal with large populations, we use a lot of heterogeneous data sources, and privacy will end up becoming a challenge. So we'll end by presenting some results where we can actually do all of this stuff with guaranteed cryptographic privacy. So basically, we can simulate populations with millions of agents, a lot of granular information, build real with streaming data coming from the world, but without ever looking at any individual agent or their interactions. Yeah, that's going to roughly be the scheme of methods that we've built in the world of large population models. And large population models, they're being used for decision making across diverse ecosystems. We're using them to understand interactions over social, financial, epidemiological networks in a lot of low middle income resources. And I would want to ground the discussion for today in the context of epidemiology, where we want to understand the spread of an infectious disease like COVID-19 on a large population. To give you some context, we'll use a simple epidemiological simulator, which models the transmission of new infections, progression of disease for each of the infected agents, and we can incorporate a wide spectrum of health and financial interventions in the system. Like every agent can you can evaluate the effectiveness of testing strategies, vaccination strategies, things like, is 2-dose vaccination better than 1 dose? What if you delay second dose of the vaccine? What happens if you use different kinds of lockdowns? And you can also quickly couple these health interventions with a wide variety of financial interventions. Like what if we give stimulus payments to people in the population? Or what happens if we have unemployment assistance for a wide variety, for an expanded section of the population? And we'll use large population models to simulate and understand the effects of these coupled dynamics. Now, when doing these simulations, the challenge is to realistically represent the dynamics and interventions, which tend to be extremely stochastic. For instance, when you take a test, it may or may not come back positive. You take a vaccine, it may or may not give you complete protection. Individuals A and B meet, it may or may not result in an infectious interaction. So there is a lot of stochasticity throughout the simulation. There is a lot of conditional operations that are happening in the simulation. For instance, on any one day of the simulation, some agents are getting infected, other agents might receive a test, others might just start quarantine after a positive test result. Some agents might get their first dose, the second dose. Some agents might be eligible for unemployment, others might not be. So there are a lot of if-else conditions throughout the simulation, and there is a lot of sparsity. For instance, some interventions will be executed throughout the simulation. For instance, every step of the simulation, some agents are getting vaccinated, but some interventions happen at very sparse intervals. For instance, stimulus payments may be given only 2 times throughout a year. So when modeling and when trying to express these kinds of agent-based simulations, the key challenge is to be able to realistically represent these stochastic, conditional, and sparse dynamics with a lot of computational efficiency. And that's sort of what we leverage with large population models. And these allow us to simulate country scale ecosystems on commodity hardware. For instance, a lot of these dynamics we use are from a popular epidemiological model in the UK called June, which we sort of redid as a large population model. And we realized that rewriting June in our infrastructure massively decreases simulation time, calibration time, and the time to do validation on a simulation on a case study while simulating millions of agent populations. So essentially, LPMs allow you to scale simulations to real country scale ecosystems with extremely practical deployment resources with very limited computational constraints. So yeah, there's a potential to deploy these systems for real world utility across several ecosystems. So the first key insight is to have tensorized and differentiable specifications. So in an agent-based model, there are a lot of agents that interact with each other on some kind of environments. For instance, a bunch of people, like individuals, meet on the street, at pubs, at schools. So there are a lot of interaction environments, and the result of these interactions cause transition in the state of the agents. So technically, the key insight is to represent agents as vectors, interaction environments as tensors, and we reparameterize all transitions to ensure they are sort of approximated as conditionally smooth operators. Basically, the key insight is to reformulate a lot of conditionals with masks and to reparameterize discrete distributions. Without going into too much detail, I'll come back to this later, but we've got an AgentTorch, a platform which provides you a simple Python API to design a lot of the computationally efficient large population models that we see, but without having to worry about all of these tensorization, differentiability, and GPU operator technical challenges. And I'll come back to that later in a bit. But the key insight of having tensorization and differentiability is that it leads to massive speed up in the simulation, and it also ensures that the runtime of the simulation scales linearly in interaction. This is extremely essential to make the simulators differentiable and to integrate the simulators with deep neural networks or to leverage any kind of gradient-based optimization. For instance, we see that we can simulate a few million interactions per second, and we can roughly simulate 5 million agent interactions in 4 seconds on a GPU over 100 time steps, which makes the ability to simulate real populations, country scale ecosystems with a lot of practical resources. So all of this computation is happening on maybe one GPU that's already there in your laptop. So you don't really need high performance computing clusters to do this kind of stuff. And the ability to execute rapid, fast simulations and to differentiate through the simulator opens up a lot of exciting possibilities, especially when calibrating simulators. So when we're trying to build simulators, a key process of using simulations is calibration. So calibration is the process of estimating the parameters of a simulator so that they are more coherent with our observed realities of the world. So just to clarify before I proceed, grad ABMs is a recurring term that you'll see throughout the slide. So grad ABMs basically mean gradient compatible ABMs, and they're like one types of large population models that we'll be talking about in the context of this talk. But if you would love to know more about what we've been doing in large population models, we've got a diverse spectrum of other large population models, some of which focus on more decentralized ABMs and a wide spectrum of other capabilities. So grad ABMs are one types of large population models. So consider an epidemiological setup where at each step there are a bunch of people in the population that meet each other. There is transmission of infection amongst the individuals, so new people are getting infected. And there is also progression in the disease stage of already infected agents. So this simulator has two types of parameters. There is theta t, which are basically parameters of the transmission operation. Specifically, it can be maybe like the R0 of a infectious disease or maybe the mortality rate, and there is theta p, which are parameters of the progression dynamic. So basically, what is the rate at which the infection of an individual is evolving? Maybe one parameter of the progression dynamics can be something like the generation time of the virus or the susceptibility across age groups, something like that. And we execute these simulations over k steps, and at the end of k steps, we get some aggregate estimates for the disease stage of different people in the simulation. So some people are susceptible, other people just got infected, they're in the exposed state. Some people have a severe infection, some agents recover, and some agents have died. So when we are trying to calibrate a simulator to historical data, we tend to have some of these aggregate statistics available in some kind of institutional records. For instance, we might want to compare these statistics or calibrate the statistics to some ground truth case data that the Center for Disease Control has recorded over time. So what we define is a loss function between the aggregated predictions from the simulator and the aggregate ground truth case data that we have. So this loss function can be anything. It could be something like a mean squared error between the estimates and the prediction. And what we want is we want to optimize the parameters of the simulation till we can minimize the loss between the aggregated predictions and the ground truth data. Now, to remind you of a nuance, the main contribution of a lot of large population models like GradAVM is the fact that they are differentiable. What differentiability really means is the ability to do gradient descent through all case steps of the simulation from the output of the simulator, the loss function, back up to the input parameters of the simulation. So basically, when trying to optimize the parameters of the simulator, I can propagate gradients through the simulator and do simple operators like gradient descent to update the simulation parameters. So this is the first mode in which we can calibrate a model like a GradAVM, basically in parameter space using gradient descent. And in practice, we realize that just the ability to do gradient descent massively accelerates calibration performance in simulations. But beyond, we can go. Are there any questions at this point? I don't think I can see the chat. So if there are any questions. Yeah, I think.
Hi, Ayush. Yeah.
Hi.
Yeah, it's good to see you. Again, basically, since you're talking about the calibration, I just have a quick question. Because like when we try to implement the grid AVM concept in New Zealand, and the biggest challenge for us is that if we add some new parameters through this process, and we notice a quite obvious gradient evolution problem through the backpropagation, which means that the gradient suddenly becomes very, very small compared to some of the others. I just wonder whether you experienced the similar thing before, or is there any potential way we can actually mitigate or reduce this gradient evolution problem?
That's a very good question. So that's a very common problem that we have also encountered in the past. So it can happen for a combination of reasons. I would love to take a look at your simulator to know what's going on. But the most common reason why it happens is because AVMs are like temporal models. They suffer with just the vanishing gradient problem that all temporal models in the past have suffered with. Like if you use any kind of recurrent neural network or something of that sort, they also suffer with problems with vanishing gradients. And the main way to get around this problem is to use these idea of receding horizons. Basically, what that means is that if you simulate too far ahead, let's say if I simulate 100 steps and I compute the partial derivative of the output at step 100 with respect to an input parameter, that's like a lot of chain rules being applied on the initial term. So since I'm multiplying everything with a quantity less than 1 at every step, it becomes really small. So the idea of receding horizon, which has become very popular and which comes from control systems, is to actually not optimize 100 steps at a time. So maybe you want to do something like this. You want to, at any point t equal to 0 in the simulator, you want to maybe use a gradient at time step. You simulate 20 step, compute a gradient, simulate 20 steps, compute a gradient, simulate 20 steps, compute a gradient. So at the end of 100 steps, you've got maybe like a stack of 5 gradient estimates. And then you can sometimes use like exponential moving averages and a bunch of other heuristics to have like better gradient estimates. That tends to be one scenario. Another scenario could be that you want to make sure that how fast infection is really spreading in your epidemiological simulator. So the gradient is a measure of like, it's also sort of a measure of like how much of a quantity you've actually computed. So if infection is spreading too slow in your simulation, it's also possible that there's basically no signal to work on.
Okay. Yeah.
So basically, maybe you want to look at like a network structure or parameters. But yeah, receding horizon tends to be like the first trick that will fix it for you.
Yeah. Okay, great. Yes, thank you very much.
Perfect. Okay, sounds good. Okay, yeah. But we can go beyond. For instance, what we did right now was that we had these scalar parameters, theta t's and theta p, that we optimize using gradient descent from some kind of a loss function. But often, because these pipelines are differentiable, in a different mode, instead of optimizing for scalar parameters, we can represent these parameters of the simulator as outputs of a neural network that can be conditioned on a wide variety of heterogeneous data sources. For instance, these heterogeneous data sources can be used to represent components of the data set or some kind of data elements which are relevant to the problem we are solving, but cannot be directly encapsulated into the assumptions of the simulator. For instance, we have things like symptom survey data coming from Facebook, some census data coming from trying to inform the demographics, some mobility data coming from SafeGraph, some insurance claims data coming from the CDC. We can use a combination of these data sources, put them into a neural network, and the neural network estimates parameters that are used to optimize the simulation. And because our simulator is differentiable, we can now optimize this entire pipeline end to end, where now instead of optimizing the parameters of the simulator directly, what we optimize for are the weights of this neural network. So we don't do gradient descent on the phi. On the thetas, instead we do gradient descent on phi, which are parameters of the neural network. And at the end of the calibration process, we've just optimized for this neural network. And this is the second mode of calibration, where you can calibrate in function space using this kind of gradient-based learning. And essentially, you're not really calibrating the parameters of the simulator. Instead, you're calibrating the generative process where the parameters are coming from. And in practice, we've observed that this process is more robust to noise, helps us overfit less, generalize better, since we can use more heterogeneous data sources and also calibrate in like a high dimensional neural network space rather than in like scalar space. And so this is roughly the core pipeline of trying to calibrate a differentiable agent-based model like GradABM. We basically use heterogeneous data to predict, let's say, infection transmission and disease progression parameters. Then you simulate case steps with the estimated parameters. End of case steps, you compute a prediction error between the aggregate statistics and the ground truth data. You use that error to compute a gradient of the loss and then back propagate it through the simulator to update the theta t and theta p parameters. And you do that for a bunch of epochs and you'll quickly get to an answer. In practice, we've realized that calibrating with these kind of gradient-based pipelines massively accelerates rate of convergence. For instance, when we were trying to calibrate an ABM to the first wave of COVID in all of London, which is like 8 million agents for 3 months from March to May, in contrast to using like a Gaussian process emulator, using gradient-based learning and this neural network pipeline reduced time to calibration from 100,000 hours on a CPU to basically 12 hours on a CPU. And it goes significantly down even with the GPU. So now you can do rapid iteration of your simulation models and make sure that they're always plugged with real-time streaming data and they're always updated. There's never the staleness of a simulator problem. And it, while also being like computationally seamless and cheaper to execute. And we also observed that these this calibration pipelines are more robust to noise and measurement errors. And what you can go beyond this, till now we were just estimating points in the simulation. Instead of that, you might want to estimate, let's say, a posterior over your simulation parameters. So that process is also very seamless. You just replace this neural network in the previous pipeline, the calib-NN, with some kind of a normalizing flow, which can be used to estimate posteriors over your simulation parameter, change your loss function from a mean squared error to something else, and then you can calibrate with uncertainty. So the pipeline is very composable, modular, and everything that's benefited generative machine learning over the last few years is going to help out with calibration of simulations. And by the way, I would love to point you out to this project, not by me, but like one of our collaborators who's built this package called Blackbirds, which allows you to do any kind of this Bayesian calibration over such differentiable simulators with just like a very simple to use API. So in case you're trying to build differentiable ABMs and you want to calibrate posteriors, do check out and go ahead and see if it helps out with your pipeline. But now we can do even more interesting things. Another interesting task that we can focus on is doing more multitask calibration. For instance, let's say we have a bunch, like let's say you try to build a simulator per city. And the thing with machine learning is that conventionally machine learning has been done on really large data sets. If I'm trying to do cats versus dogs, I've got like a few million images to work with, or most of these large foundation models have been trained on billions of tokens. But when we work with more population level decision-making problems in rapidly evolving scenarios, data tends to be very sparse. For instance, in the case of COVID, we might have a few hundred or few thousand data points per region of interest. In that case, optimizing for a single simulator can become very tough. What our pipelines allow you to do is you can also do multitask calibration over multiple simulators. For instance, multiple cities can actually come together and do a joint centralized calibration protocol where you have a shared CalibNN, which uses the county specific data for each of the counties to estimate personalized parameters. Now, these parameters can also be time evolving, run parallel simulations, and optimize the CalibNN on, let's say, the shared loss of all the simulators. So everything that you've done in the context of machine learning over the last few years, things that have made like neural networks really efficient, things like multitask learning, meta learning, transfer learning, all of them become extremely relevant in the context of calibrating large population models like GradABMs here. And you can do this kind of multitask learning where you can use data from many different counties to collaboratively train a model. And now you have a better way to join. And in practice, we realize that this calibrated model is sort of reduces overfitting for all of your individual regions, counties, cities, whatever it may be. And you overfit less across simulators. And this also provides a better way to seamlessly share data and insights across counties. For instance, if you calibrate a model on city 1 and you do not use this kind of a neural calibration, the output of a calibration is the parameters that you have, like these low dimensional scalars. So if you want to help or you want to do transfer learning to another county or another simulator, the only thing that you can do is copy the scalar values of the parameters at initialization. But with this kind of pipeline, you can actually do transfer learning by sharing weights of the neural network, of the calibration network, instead of the scalar parameters, which will help you adapt quickly to newer counties. And this is basically joint calibration in function space, which is the third mode, where you can use gradient-based calibration for multitasked calibration. So I think this has a lot of relevance in real world problem, in real world scenarios. But considering real world scenarios also presents a bunch of other challenges. Now it's possible that this data across all counties isn't located in one place. It could be distributed across a bunch of institutional silos. There's like the health department has some data, the census department has another data. There is some more mobility data coming from some private players. So what our pipelines also allow you to do, through in some of our papers, we've showed that you can actually do distributed calibration with siloed institutional data, where you can use techniques like federated or split learning to utilize siloed data across institutions and make these calibration protocols extremely practical. So this allows you to do like more privacy sensitive joint calibration across multiple institutions in this pipeline. Now the privacy challenge also comes up not just with institutional data, but it also comes up in scenarios where a lot of individual data is being used. So now to parameterize extremely realistic simulators, we're modeling interactions between a lot of agents in the population. So that essentially requires access to mobility traces of all individuals in the population. Now that can be extremely privacy sensitive and can leak a lot of sensitive data, as we've seen in cases during the pandemic. So with GradABMs or with large population models, we've also have research where you can actually execute completely decentralized simulation, where we use ideas like secure multi-party computation to execute these entire simulation and calibration protocols, but without ever making a centralized interaction matrix across all the individuals. So you never have to look at the properties of an agent or their interaction trace to be able to generate an interaction network or execute simulations. And we do not use any statistical privacy methods. So these solutions are exactly accurate as they would have been in a centralized situation. So these tools, these ways make it more relevant for real world utility. And once we've built a simulate, I'm happy to go into a lot of these methods in detail. Later, if you have questions or you can take a look at our papers, I'm very happy to talk about any of this research if it interests you. And if you've built a simulator, are there any questions till now? Yeah, I mean, I can wait for a couple of minutes if there are any questions. I don't think I can see the chat, so.
No, I think you'll be doing good. How are you doing on time? So we still have 20 minutes.
Perfect. Yeah, I think I'm good on time.
Maybe better if you go to the end, and then we can have like a discussion.
Sounds good. Yeah.
Yeah.
So, perfect. Yeah. So I know I'm going a bit fast because there's a lot of material to cover, but I wanted to give like a broad view of everything that is going on in this world, just to pique your interest. So now that let's say we've built a simulator, we've calibrated the parameters, and we want to use the simulator for decision making. Big aspect of that process is the ability to do validation. You want to know, is your simulator really giving you good answers? So validation, the way validation is conventionally done is through these idea of sensitivity analyses, which is extremely essential for validation, but tends to be extremely slow. So the main aspect of sensitivity analysis is that I want to know how would the output of a simulator change if I change some of the input parameters. So what you basically do is you have a calibrated model, you perturb a combination of parameters slightly, run a lot of simulations, get to the end, and then you measure what's the delta y, how did the output change as a function of some delta x change in the input. Now, these can be extremely cumbersome when you've got huge simulators and you need to run exponentially many simulations for every combination of parameters. For instance, this was a COVID sim epidemiological model used in the UK, where they realized that doing sensitivity analysis was extremely challenging, where the simulator had 940 parameters and they wanted to find 19 parameters which it was most sensitive to. So they ran thousands of runs to get to an answer. This doesn't really scale in the real world. It's extremely expensive, costs millions of dollars. Can we do something differently? Actually, the ability to have differentiable agent-based models resolves this problem to a large extent. So I want to remind you to these ideas of automatic differentiation that we studied back in grade school, where the whole insight is that we can compute the partial derivative of an output with respect to a large number of input parameters concurrently. So basically, because we have a differentiable agent-based model, we can do sensitivity analysis using automatic differentiation, where we can compute, let's say, the partial derivative of the number of deaths or the output of the simulator with respect to any of the simulation, with respect to a large number of simulation parameters concurrently. And automatic differentiation is independent of the number of simulation parameters. This allows us to rapidly conduct sensitivity analysis on a large number of simulators, on a large number of simulation parameters without having to run any simulation. Since our simulators are differentiable, we always have partial derivatives available at any given point in time between the output and the input. And yeah, so you can basically execute these sensitivity analyses as in this work, but without having to run a single simulation by just using the partial derivatives that are available in the simulation compute graph, since the simulator is differentiable by default. And this allows us to run a lot of real world decision making and digital experimentation analysis. For instance, we can use our simulators to evaluate prospective decisions. For instance, back in 2020, we used these simulators to ask questions like, vaccines are just coming out. What if we delay second dose of the 2-dose COVID vaccine? Now, this is a challenging question because we want to consider effects of supply chain limitations and population behavior when designing prospective interventions. And our analyses found that under some criteria, when the effectiveness of the first dose is above a threshold, you can actually delay the second dose. In retrospect, and these similar policies were deployed in several parts of the world. And in retrospect, in a retrospective paper by the British government, they realized that delaying second dose of the vaccine saved over 10,000 lives and 50,000 hospitalizations. But we could evaluate these retrospective decisions only through on-the-ground studies done by the institutions several years later. With large population models, we can actually do a lot of retrospective analyses in simulation. For instance, once we had done lockdowns and we were thinking of vaccines, we could ask a question: what really happened in the past? How effective really were lockdown policies? And the conventional way to check the effectiveness of a lockdown policy is to do something like a seroprevalence test. Basically, you take blood samples from a lot of people before and after the lockdown, and you check for antibodies before after to see what proportion of the population really got infected as a result of the lockdown. Now, this kind of an experiment requires you to go to the ground, spend millions of dollars engaging with people to collect samples and then estimate seroprevalence. because our simulators use a lot of heterogeneous, diverse, passive data sources about the population, we showed that you can actually answer these retrospective questions in simulation to quite a reasonable extent, but without having to collect any real data. So in a way, you can use large population models to muse about the past, or also even design better digital experiments, like who really to collect seroprevalence and blood antibody samples from, for instance. And we can also use these simulators to ask questions like, once we've observed the past, we saw, oh, lockdowns were great. They were actually effective, but they cost a lot of money. So you can ask counterfactual questions like, what could we have done differently? And we showed that you can design counterfactual lockdown policies, which were minimal edit, but without having to run any simulations, using the gradients and Hessians of a simulator that you've calibrated once. And given our simulators can be executed with a lot of decentralized privacy constraints, we can also use these to understand the present and analyze how infection is spreading across, let's say, different age groups and geographies, but without leaking the individual disease stage, the demographic or geolocation of any individual in the population. So these tools can become extremely relevant co-pilots for public health officials to track, understand the spread of infections and the evolution of a disease across a large population, to understand the past, analyze the present, and plan for the future, and also explore counterfactual possibilities to make smart and informed decisions. And now you might be wondering that maybe epidemiology isn't the problem that excites you, and maybe tracking the spread of COVID isn't the most exciting problem for a lot of people on call at the moment. So I want to introduce to you Agent Torch, which is our platform to design such large population models through a simple, intuitive Python API. And Agent Torch has a very generalizable design with a simple Python API that's seamlessly coupled with PyTorch. You can build simulators that scale to millions of agents. There's a simple Python API. You can seamlessly integrate AVMs and DNNs in large population models and execute large-scale simulation, calibration, optimization through a simple Python API, and can use it to design a large spectrum of simulators, do sensitivity analyses, simulations, calibrations, or even deploy them on real mobile devices if you want to do analyses in the world. And a lot of our tools are being used across a bunch of institutions and industries to make decisions to understand effect of financial, social, epidemiological networks. And we're realizing that these tools are a good trade-off to make reliable, secure decision making in low middle income resources, where you may not have have millions of dollars to build, train large foundation models, or even as much data of billions of tokens to be able to parameterize those models in the first place. And there are a lot of exciting next steps that this research presents. Maybe we can come up with ways to design more smarter adaptive agents, use this to build a playbook for future emergencies beyond the COVID-19 pandemic. For instance, after the 2008 financial crisis, a lot of the big institutions used agent-based models to figure out how to make sure that that kind of a scenario never happens again. Maybe there's opportunity to think about how we can use some of these tools to build a playbook to tackle a lot of health and sustainability challenges that are likely to arise in the world as a result of climate change. And there are also interesting technical problems to understand misspecification in a model, building trust in the outputs of a simulation, and figuring out like what North Star for all of this research should be. What's like the fully self-driving question, which has motivated a lot of computer vision research, for instance. What should motivate this research? And I'm happy to take any questions. And we have a lot of visiting PhD and postdoc positions always available in our lab. So if you find this research is interesting for you, you would love to collaborate, work with us, I'm very happy to talk further. And here's my email, and feel free to reach out at any point. Thank you. I'm happy to take any questions.
Thank you very much, Ayush. That was incredibly insightful. I'm sure that there will be lots of questions. So I just want to start with one. So when you described the the need for this, essentially describing, making your loss function differentiable, I guess that's tricky because you're trying to simulate human behavior that in some cases can be very discrete, right? Or would be better represented with a sort of delta function kind of behavior. So I wonder if that introduces any limitations, because essentially you're trying to smooth things out, right, by making them differentiable. But I don't know. I mean, I suppose that you're able to simulate lockdowns and that sort of thing, you know. But I wonder what is the, you know, to what extent are you sort of smoothing things too much, you know, in what realm, you know, you might be coming to having problems there. And related to that, essentially you need things to be differentiable so you can apply gradient descent, right? But I mean, for calibration, there are lots of other techniques that don't have that limitation, right? Like I'm thinking, you know, particle swarm optimization, for example, or other things like that, right? Like, have you, and I guess you have, like looked at, is it a problem of efficiency? Essentially, you're using gradient descent simply because it's faster, more efficient, or is there a more fundamental reason for that?
Thanks. I think that's a very important question, and that's something that we spend a lot of our time on. So on the first part, differentiating through discrete stochasticity is one of the biggest sort of technical problems that we've been spending a lot of time on to solve. And yes, so there are a lot of techniques that we've built over the time. So I mean, if you've seen there's a lot of work in ideas like Gumbel softmax, which became very popular in the machine learning community, to be able to differentiate through discretely stochastic operators, but it tends to be quite a biased estimator. And in some cases, you can actually use it. And in some situations, we realize that when you've got multiple temporal simulations, for instance, if you want to do vaccination, testing, lockdown, and you stack a lot of these continuous approximations on top of each other, your estimates can become pretty biased. To counter that, we have like a lot of newer work where we show that you can actually have low bias, low variance estimators using some of the ideas from smooth perturbation analyses. And in practice, we're observing that instead of using Gumbel softmax, using a lot of these new class of, I would say, discretely stochastic operators is doing pretty well. And we don't necessarily smooth out the distribution to be able to make those estimates. For instance, if you want to sample from a Bernoulli, we won't smooth it out to a sigmoid and then pick a smooth sample or like estimate gradient on the sigmoid. We can actually estimate both the effects of like infinitesimal perturbations, which is like the gradient at a point estimate, but we also explicitly take into account the effect of finite perturbations around like a discontinuous point. For example, in a Bernoulli, there is one point of discontinuity, and slight changes in, let's say, probability of the Bernoulli coin probability at that point can cause your answer to cause your output to have a finite change in outcome. So we've been doing a lot of research on ways to do more smooth perturbation analysis, where you can encapsulate the conditional probabilities of these finite transitions. And we realize that these give more low bias, low variance estimates. And that seems to work out pretty well for simulations. That's first part. So in summary, like a lot of work in discrete stochasticity, but I think it's worth the trade-off. It will never be perfect, but it seems to work well. And the second part is when comparing to other more emulator-based strategies, we've realized that there are two benefits. One is that gradient descent leads to much rapid convergence, as you can see in the plot here, where we compare with like a Gaussian process emulator, which seems to be pretty standard. And I think more importantly, it opens a lot of the ability to compute a gradient, opens a lot of exciting probabilities in bridging these simulators with more neural network pipelines. Now that can be an extremely powerful way to prevent overfitting to limited simulator data, or maybe you want to learn the specification to counter model misspecification, or just to like integrate your simulators with neural network pipelines, and also the benefits you get when you're trying to do like more gradient-based sensitivity analysis. So for sure, discrete stochasticity is a challenge. We're working actively to like resolve some of those issues. But yeah, I think there are a lot of benefits to the ability to having the ability to compute a gradient rather than just doing gradient-based learning or like gradient descent on the simulation parameters for neural network integrations, and sensitivity analyses.
Perfect. Thank you. Thank you, Ayush. We've got another question from Chen Wang.
Sure. Can you please speak up? I don't think I can see.
Oh, you're muted at the moment. Yeah. Good.
Hi, Aris. Thanks for the talk. It's pretty interesting. For me, myself, I have a questions because I'm pretty interested in the multitask calibration process. It's more like a multitasking optimization. So so I have a question regarding about the sharing mechanism. So in general, that's if you're learning a task, the optimize a task that definitely will help could help with the optimization with another task. But there are always some case that optimize a task needs the searching direction completed in a different way. So and I'm curious how the sharing mechanisms can help with that search.
Sorry, I think just to make sure I got your question right. Do you mean how do you make sure that you're optimizing for correlated tasks so that multi-learning actually helps?
Yes. Yes. So if the two tasks cannot, they can be correlated, but they can be either positive or negative correlated when you share the knowledge, right? So if you match to the if that match to your sharing mechanism, if knowledge are sharing among different tasks for the optimizing process, how do you design a mechanism, make sure that the similar tasks are sharing in a positive way, but the task could be like optimizing complete different direction, and the mechanism are adapt to that scenarios.
Yeah, that's a good question. I think that, yeah, thanks for the question. It's very important for a lot of these problems, especially in the context of like these agent-based models where assumptions and mechanisms across simulators can be very different. I feel that sort of is more dependent on the modeler to characterize. Like it's like any other multitask learning problem that you face in machine learning. Like if you want to do multitask learning of image classification and object detection in an image, they are correlated tasks that have a lot of insights that can feed into each other. But there can be a combination of tasks which don't sort of reinforce performance in each other. So I think it largely depends on what kind of tasks you want to optimize over. But I feel in practice, there are a large class of problems this can help. I think this can help a lot when, let's say, there are like multiple institutions or like multiple modeling groups in different parts of the country in different cities who are trying to build local agent-based models, but independently they may not have enough data to be able to calibrate a good model. In this case, multitask learning can help, especially with like our ability to do like more distributed calibration. And I think it can also, in practice, we've realized it can also help even when your simulators have different assumptions, because the two parameters that I'm predicting from the neural network for different simulators don't necessarily need to be the same. These parameters can represent different quantities from these quantities, and they can still help if sort of the tasks are correlated. You can be trying to track the spread of COVID-19 and influenza in different simulators, but they still have a lot of shared elements. And we realize that multitask calibration even helps across infectious diseases. And we've also seen like things go from like, let's say you go from COVID to an infectious disease, which isn't even person to person, because a lot of the dynamics and the mechanisms overlap. Worst case, the behavioral response of individuals overlaps. So I would say it's very case dependent when you do it, but it works in a wide spectrum of problems.
Okay, can I summarize that? So for basically your sharing mechanism is try to bring more diversity into that and the sort of the updating the parameters knowledge space. And then is that equivalent to therefore if I train each of the tasks individually, but I also can have some mechanisms working on bring the diversity will basically reach the sensing, but you can claim that your multitasking will be more efficient because they're doing several tasks at a time and also dealing with some sort of diversity in terms of the sharing. Is it?
Yes, exactly. And I would say in practice, we've also realized that the joint calibration, this mode, results in better performance on both simulators, not just faster, because it tends to alleviate overfitting, because you've got more data and like basically a less noisy gradient estimate. because these simulators are stochastic, often misspecified, and your data can also have measurement errors. So we've realized that it tends to alleviate overfitting to an extent also. So yeah, like if it fits in naturally in the scheme, there's benefits to doing this stuff.
Sweet. Thank you. Thank you for Kevin. Thanks for the talk.
Very interesting. So thank you very much, Ayush, for your time and for this presentation. I would encourage anyone who might want to ask other questions to just contact Ayush directly. And yeah, thanks everyone for joining in, and see you later.
Perfect. Thank you. Take care.
Thank you, Irish.